A phone sits untouched on a desk overnight and its battery percentage still drops a little anyway, even when doing nothing. Unplug it, glance at the screen, and it confidently tells you 43%. This is an oddly specific number for a sealed metal cell with no visible gauge, no moving needle, nothing you could physically measure by eye. So how does it actually know that number, and how can it be so precise? The secret lies not in a physical gauge, but in sophisticated electronic monitoring. A lithium-ion battery does not have a percentage built into it, it only has chemistry. Inside, lithium ions, which are essentially lithium atoms missing an electron, move back and forth between two electrodes. The anode, typically made of graphite, and the cathode, often a lithium metal oxide compound like lithium cobalt oxide or lithium iron phosphate. This movement occurs through a liquid electrolyte, which acts as a highway for the ions. When you use your phone, lithium ions deintercalate from the anode and move through the electrolyte to the cathode, releasing electrons that power your device. When charging, the process reverses. This movement is what stores and releases electrical energy. As the battery discharges, its voltage gradually drops in a fairly predictable curve. A fully charged lithium-ion cell typically sits around 4.2 volts, gradually decreasing to about 3.0 volts when nearly empty. In theory, your phone could just measure that voltage and estimate charge from where it falls on the curve. However, this method is a rough guide at best. The battery's open circuit voltage, the voltage when no current is flowing, does correlate with its state of charge. However, this relationship is not perfectly linear and is influenced by several factors. Voltage alone is a rough guide at best because it shifts with temperature, with the battery's age, and with how hard it is currently working. For instance, in cold weather, the internal resistance of the battery increases, slowing down the chemical reactions and causing the voltage to appear lower than the actual state of charge might suggest. This can lead to a phenomenon known as voltage depression. Similarly, as a battery ages, its internal resistance also increases and its overall capacity diminishes, subtly altering its voltage discharge curve. Furthermore, when your phone is actively drawing a lot of power, such as during gaming or video streaming, the voltage can temporarily drop. This is due to what's called voltage sag or IR drop, where IR refers to the internal resistance multiplied by the current. This temporary dip doesn't reflect a true loss of charge, but rather the battery's struggle to deliver power under load. So, modern phones use something far more precise, a Coulomb counter. This is a tiny chip, often referred to as a fuel gauge IC, sitting right next to the battery. Companies like Texas Instruments and Maxim Integrated are prominent manufacturers of these specialized chips. This sophisticated circuit measures the actual electrical current flowing in and out of the battery many times per second. It does this by using a precision shunt resistor, a component with a very low known resistance, placed in series with the battery. As current flows through this resistor, it creates a tiny voltage drop, which the Coulomb counter then measures with a highly sensitive analog to digital converter. By continuously measuring this voltage drop and knowing the resistor's value, the chip can calculate the current using Ohm's law. It then integrates this current over time to determine the total charge measured in coulombs that has moved in or out of the battery. Essentially, it keeps a running tally of how much charge has physically moved through the circuit since the battery was last completely full. Think of it like a water meter on a tank, rather than just glancing at the water level through a foggy window. Instead of estimating from an imprecise outside signal like voltage, it is directly counting the actual electrical charge passing by second, and subtracting that from the battery's known total capacity. This initial known total capacity is determined during the battery's manufacturing and calibration process. That running tally is what becomes the percentage on your screen, constantly recalculated as you use the phone. Even when your phone sits untouched overnight, background processors and quiescent current draw a tiny amount of power, which the Coulomb counter diligently tracks, explaining that slight percentage drop. This precise counting also explains why battery percentage can briefly behave strangely, jumping a few points or stalling, especially in cold weather or after a big software update. The Coulomb counter, while highly accurate, accumulates tiny errors over thousands of charge and discharge cycles. This is due to factors like measurement noise, self-discharge, and parasitic loads that might not be perfectly accounted for. To correct these minute discrepancies, the chip needs to occasionally recalibrate against a known reference point. This usually happens when the battery is fully charged to its maximum voltage, or sometimes when it's discharged to its near-empty cutoff voltage. During these recalibration events, the fuel gauge chip can relearn the battery's true full or empty state and adjust its internal calculations. Until that recalibration happens, the percentage is the chip's best ongoing estimate, not a perfect live reading. A major software update can sometimes reset or alter the calibration algorithms, leading to temporary inconsistencies until the system relearns the battery's characteristics. Batteries also age in a way that quietly changes the math entirely. The chemical capacity to hold charge degrades slowly over hundreds of cycles. This degradation is primarily caused by the growth of the solid electrolyte interphase, or SEI, layer on the anode, which consumes active lithium. It's also caused by other processes like lithium plating and active material loss in the electrodes. A typical lithium-ion battery might retain about 80% of its original capacity after 500 full charge cycles. So, a phone that is 2 years old may report 100% at a noticeably smaller real amount of stored energy than it did on day one. The phone's software actually tracks this degradation over time by continuously monitoring the battery's full charge capacity and internal resistance. It adjusts what counts as full based on this learned shrinking capacity. This is why an aging battery seems to drain faster, even though the counting itself hasn't gotten any less accurate. 100% now represents a smaller total energy reservoir. So that number on your screen was never a simple gauge reading. It is the result of a tiny, sophisticated chip continuously counting electrons in and electrons out. This running total is then compared against a battery's known and slowly shrinking capacity. The percentage is recalculated constantly, so you never have to think about the complex chemistry happening just beneath your thumb. If this kind of everyday mystery fascinates you, subscribe to How It Actually Works for more.